All right. This is actually one of my favorite lessons to teach. I like the mathematics of chemistry. I always like that. But what I want to show you is water is so special. It's so special. And you need to know, why is water so good at dissolving things? Now, I'm not sure how far I got the other day, so I'm just going to start all over, and we'll start over. I have a picture here. It might help a little bit. We want to take a look at water, and what we see is there's a non-metal called oxygen, and then there a non-metal hydrogen, another one, so H2O. And it seems simple. It's a simple little molecule, so why is it so important? Why is something that small very unique? And I can make a list of how many things water does that other things don't do, and it's pretty big. And so I think this is a gift. I think of hydrogen and the carbon atom as being the gift in the atomic world, and I think of water as being the gift, God's gift in the small molecule world. Maybe DNA is his gift in the big molecule world. Okay, so let's take a look. What kind of a bond would you expect to occur between a nonmetal and a nonmetal? And everybody says what? Covalent, right. Ionic is between metal and nonmetal, isn't it? And so I think it's covalent. And what happens is, one of my electrons and one of your electrons, we need to be close enough so we can share that pair. When you share a pair of electrons, that's called a covalent bond. I got it. Same thing's going to happen here. But water could have been made like this. It could have been linear. It could have been linear. Now, if God had made it linear, it would not have all the special properties. There are lots of molecules that are linear. This one's bent. It's about 105 degrees between here. And so that's important. The other thing he did was, the elements that he chose to make water out of were two nonmetals, and one of them is really greedy. Now, the fancy word for that in chemistry is called electronegativity. The oxygen's electronegativity, and what that's fancy word for saying, if we share a pair of electrons, I'm going to make them spend more time around me than they spend around you. That's the non-fancy way of saying electronegativity. So what happens is, I have my own electrons, and the one you were going to share with me, it's going to spend more time with me, and so is that one. And so what happens is, the oxygen end of water takes on what they call, in your book, if you look in the book, they have this funny symbol. It means partial. I'm not a real ion, but I have a partial negative charge. And what about these? These are partial positive charge. And so what we now have is a molecule that is polar. You say, what does that mean? What does it mean to be polar? It means having opposite ends. Now, isn't it true that one end of the water molecule has a slight negative charge and the other end has a slight positive charge? And that sets up lots and lots of neat things happening. Okay, so what happens is, if you want to say, what is the intramolecular bonding for water? Intra means within. Like intramurals, you play within the same school, don't you? If you go to college and you don't make the college team, you can play on the intramurals team, couldn't you? You play other people from the same college. Have you guys know what intramurals are? Have you ever heard of that? Okay. Okay, now, thank you. What's the next thing? I forgot. Okay, so now, what's the intramolecular bonding for water? It's polar covalent bonds. They're covalent, they're sharing, but it's not equal sharing. It's not equal. So it sets up a polarity, they call it. Okay, that's not bad. So big deal. What is that a big deal? What makes that a big deal as far as Earth and you? Well, water can dissolve many things. For example, why would water be good at dissolving ionic compounds? Here's NaCl, okay? This is NaCl. what's NaCl made of before I put it in water? I'll give you a hint. It starts with an I. What do you got? Ions. Now, if you look here, these must be the chloride ions because they're -1, and these are sodium ions here. Now, think about this. Why does the sodium chloride stay together? It's a different thing. It's not sharing. It's I'm positive, you're negative. I'm positive, you're negative. I'm positive, you're negative. And so they're attracted to each other because of different charges. Oh, so what if I throw you in water? What if this bond, what if this plus and minus is stronger than water's ability to pull me out? Then on that chart, you would say that that salt is insoluble. Water cannot pull the ions apart. And remember that chart, the solubility chart? Do you ever wonder why some were insoluble? Because they're holding themselves together, aren't they? And water's ability to pull them apart is not great enough. Well, what about NaCl? That says soluble. What's that mean? Water can pull you apart. Now, which end of the water molecule would be attracted to a chloride ion, a negative chloride ion? Which end of the water would be attracted to it? The hydrogen end or the oxygen end? The hydrogen end, because the hydrogen end is positive, isn't it? And so that's why the drawing shows the hydrogen end being attracted here, and another one, and another one, and another one. And I don't know the exact number, but when enough of them get there, it will be stronger than the bond of Na and Cl. And it will put it in solution. This ion will be completely solvent. I think they used the word, did they use that word here? I have to remember, I have an advanced chemistry book and I have this one. Okay, I don't see it here. Okay, but it's actually in solution, and and you can see the picture that it's the hydrogen ends that are attracted to the chloride ion. And what happens to the sodium ions? Well, the oxygen end is attracted to those, and it pulls it out of solution too. And so what we have is a solution of sodium chloride, which actually has, don't tell anybody, it has no NaCl in it. There's no NaCl in salt water. There's Na ions and chloride ions, and they're not even together, are they? They're not even together. So it's a solution of ions. Remember that chapter we talked about electrolytes? That's why electricity can go through it, because there's a bunch of ions. See that? Now, I'll show you one other thing I think is kind of amazing. What happens, what would the intermolecular bonding be for water? What if water gets next to other waters? Intermolecular means between water molecules. What? Is there a bonding? Is there a bond between water molecules? Yes. There's an attraction there. And so the negative end, the oxygen end of one water molecule will be attracted to the hydrogen end of another water molecule. And that's a real famous bond. If you do become a science major, if you go to college and do biology or chemistry, I don't know if Miss Founds used this word with you or not. Did she ever use the word hydrogen bonding? Have you ever heard that word? Did you ever, I'm going to flip this over. Did you ever do this stuff in class where you had DNA and you had A here, T, G? Did you ever have that? And what was over here on the other side? Do you remember DNA? Uh-oh. I know you did. Was that during quarantine? Okay. Well, do you know what DNA is? Okay, well, DNA has these bases, and this is called the genetic code. Okay. Well, on one side of the DNA, if you have adenine, then you have over here called base pairs with thymine, and thymine base pairs with adenine, and guanine with cytosine, and there's these attraction, you see? And guess what kind of attraction there is between these bases? It's not a powerful bond, and God made it that way. God said, I want this thing here to be powerful. That's covalent bond. But I want the bond between the bases to be not that powerful, because I want the DNA to be able to open up, unzip it, and put it back together. And this is hydrogen bonding. It's the same thing. When you get a lot of things together, hydrogen bonding can make a difference. Now, Have you had this at all ever? Have you ever had about the polarity of water? Have you ever had that? Okay, I need to. You can shake your head or just say, do something. Have you had polarity of water? Okay, so you know that when I put a piece of water on wax paper, especially, why does it form a bead? Why didn't it just flatten out? And it's this stuff here. It's hydrogen bonding. When you're doing the insect collection, and the insect, you saw an insect walking on the water, and you thought it was a water spider, but it's actually a water strider. Isn't that right? Wasn't it? What's it walking on? They call it surface tension. What's surface tension? Hydrogen bonding. That's why if you want to make an insect trap, here's what you can do. Pan of water, big piece of glass here or plexiglass, and then you put in the woods, and these fast-flying insects will hit the glass and fall in the water. But they'll escape because they can get to the edge. See that? So what you do is put a couple of drops of dish detergent in the water. What is dish detergent? It breaks up the hydrogen bonding. Now the insect hits the glass, goes down, and blah, 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 goes to the bottom, drowns, and you got yourself an insect. And that's what dish soap does. There's so many experiments on YouTube. They're kind of neat. You can take like a bowl of water and put pepper on it. I had a pastor do this once. I did it in class once, and their kid came home and said, "Can I do that?" Yeah. So you put pepper on there, and they talk about people getting along and stuff like that. And then what you do is you have a little sliver of soap, like you had bar soap, and you said, "What happens when I do this?" And what he did was he pretended like a black person or a white person, whatever. He was doing something about prejudice. And you put that little piece of soap right there, right in the middle, and all the pieces of pepper will go away like that. Because what happens is you break the surface tension here, and there's still surface tension pulling on it there, and it pulls all the pepper out. Do that at home tonight. It's really neat. A little bowl of water, pepper on it, all right? A little piece of bar soap, put it right in the middle. You'll say, that's magic. All right. Well, anyway, that's surface tension also, hydrogen bonding. Okay, so one thing I want to show you, and I'll get to the last part here very soon too. This is the part of the lesson that will be the hardest for you, but I'm going to try to make it as simple as I can. Did you know that if you're not absolute zero, they think that every particle has some kind of motion to it? Have you ever had a teacher talk about that where, and then they said maybe, did they ever tell you that like solids are moving a little bit and liquids are moving faster and gases are really, see that? Have you had a teacher do that? Now, they might not use the technical word, the kinetic theory of matter. They may not have said that, but that's the theory. Now, so here's my question for you. What is the molar mass of, let's say, carbon dioxide? What's the molar mass of carbon dioxide? And it is 44 grams per mole. Now, that mass, I'm a little physics here, okay? A little bit of physics. How much kinetic energy would that have? Well, you can stick it in the equation, and it has a lot. It has a lot of kinetic energy at room temperature. So at room temperature, carbon dioxide has so much kinetic energy that it cannot be a liquid. It cannot be a solid normally, dry ice is, but it's a gas. Okay, so what happens if I take a smaller mass? Let's try N2. You have a molar mass of only 28. So you have smaller mass. You're moving even faster. You're moving even faster. And so if carbon dioxide couldn't hold itself into a solid or liquid, you're not going to. Let's go heavier. Let's go real heavy. This is called butane. Butane is found in lighters. The only reason it looks like a liquid is because under pressure, but if you let it out, it's a gas. This thing's really heavy. It's moving slower. 58 grams per mole. And you know what? If there's anybody who had a chance of being a liquid, it would be that, but it's not. Room temperature says, sorry, that's too much kinetic energy. You have to be a gas. And I want to show you something here, okay? I can do oxygen. It has 32. It's a gas. Ammonia, 17. It's a gas. Hydrogen, of course, it's a gas. It's really tiny. It's really moving. And then I want to ask you this. It seems like all the way up to 58, if you're only as big as that, even up to 58, you have to be a gas at room temperature. You have to be. You have to be. And what is the molar mass of water? What is the molar mass of water? What is it? 18? Then you have to be a gas. This should not happen. Water should not ever be a liquid. There should be no liquid water on this planet. That means no oceans, no clouds, no you. You should not have any liquid water in you because the kinetic theory says you have to be a gas. Now, I want you to think, what is it that makes water not a gas? There's something that's holding it together so it won't be a gas. And what do you think it is? Even though I said it 5 times a day. What is it that makes it into a gas? Hydrogen bonding. And that extra pull between one molecule is going to attract another. And the kinetic theory says, you need to be a gas. No, my neighbor's pulling me and keeping me into a liquid state. And it's amazing to me. I don't know of any other material that light, that is a liquid. And yet, you have a lot of water in you. The planet has a lot of water in you. It's amazing. Let's go one more. We're almost done with this lesson. And I'll leave you alone after that. Alcohol. Alcohol? Talk about alcohol. A lot of you don't know what alcohol is made of. I'll tell you that alcohol is made of carbon, hydrogen, and oxygen. Okay? And there are different kinds of alcohol. This one has to be called ethanol. Ethanol is the kind of alcohol they put in mixed drinks and stuff like that. Okay? So, ethyl alcohol, it should be a gas. But let me show you how it's made. Carbon, hydrogen, 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 carbon, hydrogen, oxygen, hydrogen. Now, we already know this story here. What happens when oxygen forms a bond with hydrogen? Is it going to be an even sharing? Or is it going to be a polar nature? Is one end going to be slightly negative? And so alcohols should not mix with water, but it has this one part that's polar, and it has a plus-minus nature. All right, look again. Water has a plus-minus nature. Ionic compounds have a plus-minus nature. No wonder it can dissolve a lot of ionic compounds. This is not ionic. This is a molecule. It's molecular. Why can it dissolve alcohol also? Because this is polar and water is polar. So water can dissolve things that are ionic, things that are molecular. See that? That's why it's called the universal solvent. So a couple more and we'll be done here. You know what sugar is? That was probably COVID. I don't know if that was COVID or not. Did you guys do a biochemistry unit where sugar, do you know that sugar is made of carbon, hydrogen, and oxygen? Do you know that? You know what carbohydrates are? Sugar is a carbohydrate. Okay. Wait. Even if you don't, I'll help you. This is the stuff you put on, this is called table sugar. It's called sucrose. This is stuff you have in your home. And it's made of carbon, hydrogen, oxygen. But why does sugar dissolve in water? And if you look, you'll see it. I circled them. Look at that. COH. O bonded to H. O bonded to H. O bonded to H. O bonded to H. And what kind of a bond is that? Is that going to be a even sharing, or is it going to be polar? And so every one of those points of sugar is going to have a plus-minus nature to it, and that means water is going to be able to dissolve it. This is amazing. And I'm going to show you one. I'll show you one that it won't be able to dissolve. And if you look here, this only has carbon and hydrogen. Carbon and hydrogen. And when they form covalent bonds, hey, let's kind of share evenly. And that way no part of this molecule will be plus or minus. Did I do this demonstration for you last week? Okay. So this has a plus-minus nature, right? And what is this stuff? This is called hexane. Hexane is this stuff here. It's C6H14, and it only has carbon and hydrogen. That's all. It's called a hydrocarbon. Gasoline is a hydrocarbon. Oil, hydrocarbon. See? Vegetable oil, hydrocarbon. And so they only have carbon and hydrogen, so there is no polarity. There's no plus or minus nature. And so will water dissolve those? No. And so the other day when I put these, you sure? I'll show this to you, right? You sure? I show it to you? Did I pour this into there and I pour this in there? Wait, I'm looking. Were you here? Oh, you weren't here. Okay. I'll do it one more time. So here's something that has a plus minus nature. It's called water. It's polar. Here you go. And then this stuff has only carbon and hydrogen in it. And it's going to be called, they call it non-polar. Okay. So here, this is only has carbon and hydrogen in it, just like gasoline only has carbon and hydrogen in it. Lighter fluid only has carbon and hydrogen. Anyway, I put this in there. And will water put it in solution? Will it mix and form a solution with water? No. See that? And that's pretty weird when you see that. This is less dense and it won't mix. Even if I put the lid on. Here you go. I'll turn it upside down. It's still not going to mix. It's still not going to mix. You see that? And so this is polar and this is non-polar there. And that's kind of a big deal in the world of chemistry and biology. Whoa. Got to put the top on. There you go. Okay. Now, and then the last page, it does show vegetable oil. And guess what vegetable oil is made of? Only carbon and hydrogen. And so when you put vegetable oil in water, it does not mix. It sits on top like that. Everybody got it? That's pretty much it. That's it for the chapter. Okay. Did I give you a practice test? Did I give you a practice test? Okay. I don't think I have one. Let me think about that. Yeah, that's what I mean. Yeah, that's what I meant. Okay. You have the rest of the period to work on that. That is due on Wednesday. And then, yes. Yeah. Okay, so you have the rest of the period. If you want to sit with somebody, you want to look over that homework and say, I didn't get this question here, and I'll be done. So I am done.